Welcome learners. In today's lecture, we are going to start the fifth chapter of our main textbook, Engineering Electromagnetics, ninth edition by William Haight and John Buck. And in this chapter, we are going to look into materials that are widely used or day-to-day used by engineers around the globe. Till now, we have learned different techniques where we can find the electric and magnetic field interacting with each other, especially the electric field intensity and its constituent, that is the electric flux density. Now we want to see how these parameters or fields are integrated and how they cooperate when we deal with materials such as conductors and dielectrics. In the first part of this chapter, we shall talk about the conducting materials, how these are defined to be conductors, what happens when current is excited by an applied field inside these conductors. We are also going to look at the Ohm's law, evaluate the resistance of these conductors, and finally conclude the first part of this chapter by looking into the boundary conditions when dealing with conductors and free space. In the second part of this chapter, we are going to build our understanding about dielectrics and what is the thing that differentiates a conductor with a dielectric, or also known as insulator. Just a hint, these are no free electrons available inside the dielectrics, or the charges are so much tightly bounded inside the dielectrics that they don't get polarized, and thus no conduction of current exists. Again, with this part of the chapter, we are also going to look at some of the parameters such as electric dipole, permittivity, polarization, and then we are going to conclude with the boundary conditions of dielectric materials. Before we begin, a few thing to remember is that most materials possess both dielectric and conductive properties. Materials considered dielectric may slightly be conductive, and a material that is mostly conductive may slightly be polarized. But it is up to us and the excitation techniques that basically give us the pure conductor and a pure dielectric. We will look into these conditions or the lattice structures through the contents of this chapter. So in this chapter, we are going to start our discussion with what is a current, which most of the engineers know from their basic understanding of physics and lower level courses. Then we are going to talk about the current density, and then we'll conclude this lecture with continuation of current, and then we'll add few problems for better understanding of all of these topics or the equations that define these topics. So let us begin with the first topic from this chapter, and that is electric current. So we already know about this topic, but before going to current, keep in mind that we discussed charges, or we discussed a charge in the static position. All our discussion previously has been on the static charges, but what happens if these charges start to move? So whenever charges are in motion, it gives rise to something we call as current, represented by the symbol I, and it encompasses unit of amperes, also as coulombs per second, but in most of the literature we use the unit of amperes with the symbol A. That represents that this entity is a current. So we can say that current is basically the rate of change of charges, rate of change of charges. So we can say that current is the rate of change of charges, or charges passing through a specific area in a given amount of time. As we can see over here, we consider a piece of a conductor. Let us say this rod is a piece of conductor, and the charges inside are moving as per reference time, and we can say that conventionally this is the positive side of the conductor and this is the negative side. The positive and negative side constitutes that a source has been applied in the form of a battery, and we can see that the charges move from the positive towards the negative side. This motion of charges constitutes what we call as a current, and if we focus on this region, we can see that the charges are moving from the positive to negatives in a conventional way. If we talk about the current knowledge, that is, the current is normally created with the flow of electrons, which is from negative towards the positive. but we'll stick to the conventional method where the charges are moving from the higher side, which is the positive terminal of the battery, towards the negative side. So this is what the current is. It's the rate of change of charges with the unit of ampere. Now, once we know this, we come to what is known as current density. So why we want to study current density? Again, in the course of EMT, we are mostly interested in events occurring at a point rather than a larger region. And this goes without saying that all the proofs we have done in the previous chapter, we always first figure out what is the smaller effect of that field, and then we move towards the larger effect, that is, we go towards the integration of that field. So in the same way, the current is taken as a larger entity when it is moving inside any conductor element. We basically want to begin by first focusing at a smaller point, and for that we use the term of current density represented by symbol J, and the unit is ampere per meter square. So the current density's unit is ampere per meter square and the symbol is J. So now and remember, it's a vector quantity. So now what can we say about the current density? So now let us take a conductor here as shown in the image. So these are the lines or boundaries of the conductor, and a current I is flowing through it. So current I is flowing inside the conductor. We know that current is basically combination of charges per unit time, or is the rate of change of charges. Now inside this conductor we select a small region shown over here, and we focus our attention on this small point inside the conductor. So this green highlighted point is where most of the current is densely formed. So we can say that this dense area is the concentration of the current inside the conductor at a specific point in time, and the output from this green area is something what we term as the current density J, and you can see it is in parallel with the initial current I. Since the current density is visually seen as such, we can represent it as mathematically that current density is basically defined as the rate of change of incremental current. So this is a small current, incremental current, because we are focusing in a region crossing an incremental surface, which is represented by delta A. Sometimes it is represented as delta S for the surface. So rate of change of incremental current per unit incremental surface is known as current density, and if we apply the limits on it where the area is getting small and small, this means that this green region may move inwards towards a certain point when the value of the area tends to 0. This means that we can focus ourselves to a specific point inside the conductor. So this is what this limiting is saying. So generally speaking, current density is basically the rate of change of small current per unit small area, either represented by delta A, or in some books in literature it is represented as delta S. So this is the current density. Now if we further look at the current density, it can have different behaviors as such. The current density, let us say if I have this coordinate system, this is my y, this is x, and this is z, and this is an arbitrary surface S. So if the current is moving in the upward direction, or we say it is perpendicular, and if we select a small region or surface over here, which is our small area, let's say delta A or sometimes delta S, then the output of the current from this area is represented as J, and you can see that the current density J is perpendicular towards the surface, which means that surface sheet or the component of J will also be a unit vector which is normal. So I can say that my incremental surface current density could be represented as J normal is equal to ratio of delta I by delta S, or I can say that delta I is equal to normal current density to the surface, and we already know that the effect from the surface is always normal or represented as the unit vector normal. Similarly, if I further elaborate this position of normality into its components, so I can write delta I as J of n along normal vector dot product of S of n along the normal vector. So the dot product of the normal vectors will be 1, so I can write it as J of dot product with delta S. So this means that the current density can have two variations. The first could make an orthogonal angle of 90 degree from the surface, and the other could be the current is along the surface. So if this is the surface and the current is moving in this direction, so the object from the surface will be normal if this is our surface, but the current density can have a different value as well, which will be from here. So again, this variation or angle can be normal to the current density, which is shown over here as A, or it can be equal to it, where the cos angle will be 0. So these are the two representations of current density within a small surface. And similarly, if we want to find the effect of the overall current inside the conductor, then we can use this equation that gives us the total current passing through any area, which is the integral or a surface integral of the current density with the dot product of the differential surface element or the small surface. So this is the current density that we have, and we have seen this visually and with the expression as well. So let us look at an example where this current density is practically utilized. So consider we have a coaxial cable carrying a 20 ampere of current along the Z direction. The radius of the inner conductor is A, and which is having a value of 20 millimeter, and the outer conductor has two radiuses. The inner portion is having a radius of B of the outer conductor, and the outer portion is having the radius of C. So this is the outer side of the outer conductor, and this is the inner side of the outer conductor. And we want to find what is the current density of both of these conductors. So this is where the current density becomes viable. So in order to find the current density, we use the equation current density is equal to the current passing through an area of A. So if we want to find the current density of the inner conductor having the radius A, so we just use the value of I by A, and area of the circle is pi r square. So we get the value of pi, and we convert 20 millimeter into meter, so it is 0.02 whole square, and we get the value of 15.9 kilo ampere per meter square in the direction of AZ, because current is moving in the Z direction. Similarly, for the outer conductors, we can find the current density J by just taking a difference of these conductors, the inner and outer part, and we'll get the answer of 19.5 kilo ampere per meter square, again along the AZ direction. So this example basically tells us where in practical life the current density can be utilized, or one way we can find the effect of the current in specific areas, which is the current density. Now let us look at the current as a velocity for volume charge distribution. In other words, we want to basically understand the relationship between current density J and the volume charge density rho V. So this is what the topic is all about. So current density J and volume charge density can be represented by looking at the example shown below. So let us say that we have the rectangular coordinate systems as x, y and z, and a cube is placed at the origin. So at time is equal to 0 instance, the cube is at the origin, and the length it is covering along the x-axis is from origin to this point, which is delta L, and the front face is basically the surface sheet represented by delta S. So it is covering the z and y axis, and delta L is along x-axis. Now at time t is equal to 0, this is where the cube is in a stationary position. So if I want to find the effect of charge or incremental charge or differential charge of this cube, I know that the differential amount of charge or small amount of charge is going to be equal to rho v into dv. So this is the amount of charge, let's say, present over here. Now after certain time instance, the cube moves, and that time instance is that we move from t is equal to 0 to any time of delta t. We see that the cube has moved from the origin to a certain point that is covered as delta x. So this is the amount of shift that has happened along the x-axis at time is equal to delta t. And this could be a byproduct or effect from any current that has filled or performed an action on that. So in any case, the cube has moved a certain distance which we represent from the origin as delta x, but the original length remains the same, which is delta L, and the surface sheet remains the same, and the charge delta q will also remain the same. So now what has happened? So we can say that this region over here, or this region, is the region where the change has happened, or where the distance has been covered from the origin, or the cube has moved a certain distance in this direction from the origin. So now how can we find the current densities effect as per the charge distribution of this cube? So let us look at it mathematically. So here you can see the 3D view and the XYZ plane view of the cube which has moved. So this is delta x from the origin, and this is where the charge, where the cube has moved a certain distance. Now we know that the charge or differential amount of charge is rho v, and what is delta s and delta x? So we can understand it this way. So we know that the amount of charge when the cube was initially at rest was rho v into delta v, and when the cube has moved, we know that the volume is basically length into width into height. So this is basically the product of the length and the surface area. Surface area is covering your width and height over here. So this is how we got delta s or delta x. Since we have moved a distance of delta x, so we replace delta s with delta x, and this is now our charge value as shown over here. Now let us see what is the effect of the current density in form of the current. So we know that the current is represented as the ratio of rate of change of charge. What is the value of q? This is the value of q. We input the value of q over here. So this is rho v delta x, and we can see that we have a value of delta x divided by t. This is distance per unit time, which is nothing but velocity. So we can say that the total amount of current, or the differential amount of current, not the total, is dependent upon the volume charge density, the delta s, which is the surface area over the front, which is shown over here, and with multiplied with velocity. Now since we want to find the relationship with the current density, so we can say that the current density is the ratio of current over S. So from this equation, we'll just bring delta S over here. We'll be left with rho V into V of X. So this is the relationship between current density J and the volume charge density rho V, dependent on the product of V. So what is the meaning of this statement? So the equation is J is equal to rho V into V. So this statement is basically telling us that the charges are in motion, or the constitution current, where this, so this basically tells us that if we have a portion of the current which is the current density, it is equal to the charges which are in motion. So this is what is the relationship between current density J and volume charge density, which is rho v. So hope you got the idea and exact meaning of the equation, and it is the same equation saying that the current causes the motion of the charges and the current density is doing the same thing. And this is the equation that we have. Okay, so now let us look at a problem and see how we can find the current density. So in this example, or in this question, we have been given the current density J, that is in the A rho and A phi, so there is no A theta, and we have been asked to find the current density at point P. Then in the second part, we need to find the total current flowing. So this means we need to integrate outward through a circular band. Okay, let us do the first part. Okay, so in the first part, we need to find what is the current density at point P. So this is straightforward. We have the value of current density. So let me use this space. So it is 10 rho square z along A of rho minus 4 rho cos square phi along A of phi. So just input the value of rho and phi over here. So rho is 3, phi is 30, and we don't have the z component. So J at point P is going to be 10, then the value of rho is 3 square, and z is 2 along A of rho minus 4 into 3 cos square phi is 30 degree along A of phi, and it comes out to be 180 along A of rho minus 9 A of phi meter ampere per meter square. So this is the value of current density at point P, and we can verify that this is the answer that we are getting for the first part. Now in the second part, so let us now go to the second part. In the second part, we have to find the total current, which means we have to use the equation of the integral, or a surface integral is J dot d of s for the current that is flowing outward from the circular band. Okay, this means that if I draw the circular band, so this is my x, y and z, sorry about that, this is my x, y and z, and we know that this is the cylindrical coordinate system because we have rho, phi and z. So z is from, let us say, from 2, so 2 to 2.8, let us say z is from 2 to 2.8, this is the z axis, and rho is something like, so it is going to be a cylinder where the value of rho is over here, and the current is moving away from the circular band as it is mentioned in the question. So how much current is flowing? Again, the value of phi is from between 0 to 2 pi, so we basically form a cylinder. So in this case, we just apply the equation. We already have the current density value J. We just first need to figure out what is ds rho. So ds along the rho will be, because the rho component is just the fixed component and rest of the values are given to us, so it is going to be rho d phi d of z along a of rho. So this is the differential surface element for the cylindrical coordinate system. Once we have this, we just apply the integral, that is going to be a surface integral of j dot d of s, which is basically a double integral, and the limits will be something that is varying, which is along phi and z. The value of j will be 10 rho square z along a of rho minus 4 rho cos square phi along a of phi, and what will be ds dot, so I'm going to do dot product of rho d phi dz along a of rho. So this is the value. So now current comes out to be, in this equation I can multiply rho with rho square, so it will be rho cube, and my integral will be, so a rho and a rho will be 1, I'll be left with d phi. So the equation that I'm left with is double integral, phi is from 0 to 2 pi and z is from 2 to 2.8, and the value I have is 10 rho cube z d phi dz, and don't forget that we have meter here, so into 10 raised to power minus 3. Now we further integrate it, so 10 is a coefficient, will come out with rho cube as well, so it is going to be 10 rho cube, and if we integrate it with phi, so it is going to be 2 pi, so I can, or okay, first I'll put the limits so it becomes easy for you, then in the later problem for the z it will be z d of z, and for the rest it will be 0 to 2 pi d of phi. So this is what we'll have, and don't forget 10 raised to power minus 3. Now this will be 10 rho cube, so this portion here will be 2 pi, and this will be z square by 2, and you put in the limits of 2 into 2, so this will be from, so this comes out to be 2 point, sorry, this with me, okay, I'll write it over there. So for it will be 2 pi, and then for the z it is z d of z, it is 2 to 2.8, and this now becomes z square by 2 with 2 to 2.8, and this comes out to be 3.84. So finally, once you have everything, it will be, you put in the value of rho, which is 3 cube, and then you have 2 pi into 1 by 2, 3.84, and don't forget into 10 raised to power minus 3. Finally, the answer comes out to be 3.26 amperes. So this is the total amount of current that we are getting, and it is the same as shown over here. So this is the solution of using the current density to find the total amount of current. Now let us come to the next part of this lecture, and that is continuity of current. So to understand continuity of current, we need to revisit the law of conservation of charges. And if you remember that charges can neither be created nor destroyed, although equal amount of positive and negative charges may be simultaneously created by separation among the charges or destroyed by recombination. So this is what the charges behavior exists. The same logic is now applied to what happens if we have any enclosed surface. Let us say this is an enclosed surface, an arbitrary surface, and we want to see what happens when the current enters through this surface and it leaves in the form of either the output current or in the form of current density J from small patches. So if we select small areas, and these areas again is small d of s's, and the current enters over here and it leaves through these d of s's in the form of current density, then what is actually happening? Are the charges getting emptied from this surface? So these green dots may represent the charges. So what is happening inside? So in order to understand this, we talk about continuity of current. So we say that the total amount of current entering through any surface is represented by the equation we just saw. So the surface integral of the current density and the dot product with the differential amount of surfaces or incremental surfaces. We can say that this behavior can also be represented if we take the rate of decrease of charges per unit time, and the negative sign is basically shows the decreasing rate. It means that if the current is created by charges per unit time and the same current is entering this surface, then the current that is leaving will be equal to the amount of charges that are leaving the surface, which is represented by the right hand side of this equation. So it means that the total net charge is 0. The amount of charges that enter as a I is the same which is leaving out either in the form of J, or it can be in the form of complete current, or it can be represented in the form of decaying charges as shown over here. So this is the continuity of current which enters from one terminal or one input and leaves from the other terminal or the other output. So this expression basically gives you the continuity of current equation, and we can further simplify this equation as well in the form of current density. How? So again, writing the equation as we saw previously, and then we analyze two parts in form of the color coded scheme. So let us first focus on the red part. So we know that this is the surface integral, and if we apply the divergence theorem, we can convert the surface integral into volume integral. If you remember, the divergence theorem shows the equation between the surface integral d dot d of s is equal to the volume integral divergence of d into dv. The same thing has been done over here. Instead of d, we are using j. So this surface integral of the current density is represented by the divergence of the current density in the volumetric domain. And on the right hand side, this decaying charges per unit time is basically represented again in terms of volume, because we know that volume charge or charge is basically volume into dV. So this is, or if you don't remember this, this is like volume charge density is the number of charges per unit specific volume, which is dV by dq. So this is what is happening. So we have represented q over here in forms of the volume charge distribution in a specific or small volume dv. And what we have done now is we have changed this d by dt to a partial derivative. And why we are doing this? Because if you remember, d by dt gives you the reference from x, y and z. Let's say if we have an x, y, z coordinate system, or let's stick to this image. If this is y, this is x, and this is z. So d by dt means that we are differentiating something with respect to x, then with y and with z. So it is dependent. But if we are just focusing on one of the x's, then we can represent it with a partial derivative. So this is why we are moving from d by dt to a singular location, which is the partial derivative, and it is also verified over here. Let us say if the current I is entering from here and we are just focusing on this small surface, which is our d of s, then we want to just see what is the output from this surface in this particular direction. That will give us j. So just if we are just focusing on a particular direction, then we use the partial derivative as shown over here. That's why we have change from d by dt to the partial derivative. Now we can compare both sides the equation. The updated equation is the volume charge on divergence of A dV is equal to negative volume of the partial derivative of the volume charge per dt into dV. So when comparing these two, I can get rid of these values, and thus finally I will have the relationship of the current density in terms of the volume charge distribution, that is partial derivative of V by T, and this is my new relationship between the continuity of current, or I can say this is another way to represent the continuity of current in terms of the current density, which is J, and this is known as the point form equation of the continuity of current, and this is known as the integral form of equation of the continuity of current. So what does this point form means? It means that the small volume is considered in a bigger volume. A small volume is considered in a bigger volume, and the current which is diverging from that smaller volume is equal to the rate of change of decay of the smaller volume charges, and it is the same thing as we saw of the charges decaying from the main current source. So hope this clears the continuity of current concept. Let us look at a problem and see how we can utilize these equations to get the solution, especially the point form of continuity of current. So in this problem, we have been given the current density in the cylindrical coordinate systems. It is in the AZ direction with phi range given. Now in the first part we need to find the total current, which means we need to use the integral equation of the current on the surface of 0.1 meter along the AZ direction. In the second part we have been given the velocity at 0.1 meter and we need to find the volume charge density, and in the third part, if the volume density is such, find the charge velocity there. Okay, so let us start with the first part and use this portion. Okay, so in the first part we need to find the total current. So we know that total current is equal to the surface charge closure of the current density, and since we are just using which direction, this region, find it in the AZ direction, which means that d of s in the z direction will just be rho d phi and d rho with the normal of AZ. So this is the differential surface representation if the direction is along the z-axis. And what are we having? So if we draw this for better visualization, this is our y, this is our x, this is our z. We can say that our cylinder is something like this, where this is our rho and it is from 0 to 20 micrometer. The current is moving in the upward direction along AZ, and if we are if the rho is value is greater than 20, then in this case the current density is 0. It makes sense that if we are outside the cylinder, there is no current density. The current density is only going to exit inside the cylinder. Okay, so let us solve this integral now. So I will be equal to double integral. We know that z is the direction of the current is along z axis, so the variation will be only in rho and phi, and the value of j is minus 10 power 6 z power 1.5, and what is a of z, and what is okay, I'll write a of z dot product with j. So j is going to be rho d phi d rho along a of z. Okay, so then I equals to, let's put the limits. Rho is from 0 to 20 micro and phi is from 0 to 2 pi, and the value will be minus 10 power 6 z power 1.5. d az and az will be 1, so I can write rho d rho and d phi. This and this dot product is equal to 1. Now we can solve it. So I equals to, just bring the coefficients out, which is minus 10 power 6. So z is not being integrated, so we can add the value of z, which is 0.1, so I can write it as 0.1 power 1.5. so these are the coefficients, and then integral will be along d phi and d rho. So d rho will be rho square divided by 2. This is from 0 to 20, and we multiply it with d phi, so it is going to be 5 from 0 to 2 pi. These are the integral limits. Then I can just write it over here. It is going to be, so once I solve the upper value, it comes out to be minus 31622.7, and in parentheses I will have 1 by 2 4 into 10 raised to power minus 10 into 1, so it is going to be 2 pi. So this is going to be 2 pi. So this is inside the parentheses, so 2 can cancel out with 2. So the value of I then comes out to be, once you solve this equation, the value will be minus 39.7 into 10 raised to power minus 6 amps. So this is the solution to the first part, and we are getting the same result. The micro is 10 raised to power 6. Now let's solve the second part and the third part of this problem. So I'll change the color so we get better understanding. Now solution to part B. So part B is find the rho v. So we have been given velocity as 2 into 10 to the power minus 6 meter per second, and z is at 0.1 meter. We need to find rho v. Okay, so we can use the equation that shows the relationship between current density and charges in motion. So from this equation we can find rho v, which is basically the current density or velocity, and once you input everything over here, the value comes out to be, so I'll just input the value for easiness. Rho v is equal to, value of j is 10 raised to power 6, and we can put in the value of z as 0.1 power 1.5 divided by velocity is 2 into 10 raised to power minus 6, and it comes out to be minus 15.8 meter cube per meter cube. So this is the answer for the second part. Similarly, for the final part, we need to find the velocity when the value of z and the rho v is given. So it's the same equation. We know the relationship between the current density J is equal to rho v into v. Since we want to find v, it is going to be J divided by rho v. And you input the values and the answer will be 29 meters per second. So this is the velocity for the third part, and hence this concludes the solution of this problem. Now let us come and discuss the material properties at the microscopic level, and this is something you might have seen in your previous electronics course, but again just to give you a recap, that what is the difference between an insulator, a semiconductor and a conductor in terms of the charges that reside inside the material, and if an external energy is provided in the form of a voltage or heat or light, what happens to those charges. So if we talk about conductors, we can categorize them into two different layers, where the first layer is called the valence band, where the charges reside, and if we apply an external force, that external force can be a potential, a light source like a photon, or it can be heat. It basically excites these charges and they jump from their valence shell to what is known as a conduction band, and here these electrons become free and then they can conduct or form different bondings. So you can see that the layer between the conduction and the valence band is so thin that the electrons, even with a slight excitation, temporarily can jump from their rest state to motion state, and hence we say that conductors are good form of electricity, or they are easily allowing the charges to flow inside them. When we talk about insulators, again we have the same two bands. One is the valence band or the rest state, or we can say the idle state, and once the energy is provided, they have to jump from the valence band to the conduction band. However, the gap between these two bands is so large that you need immense amount of energy for these charges to reach over the conduction band, and since the energy is all the time not available, that's why we say that insulators don't conduct charges easily. They are normally polarized, or they are stick to their crystal lattice or molecular structure. So insulators have this property that the energy or the band gap is so much that you need vast amount of energy for the charges to jump from their rest state to the motion state or active state, which is not easily attained in insulators. However, if we do attain that form of energy, we come to a third kind of a material that is vastly utilized in electronics industry, and that is semiconductor. The beauty of semiconductor is that its band gap is acceptable, and amount of energy is available externally that can excite these charges from their rest state in the valence band to jump to the conduction band, and thus they become free electron, and then they can conduct or make bonding with their atomic structures or any other molecules for that matter. So these are the three internal or microscopic conditions of how the conductors, insulators and semiconductors behave. So keeping our study strict to conductors for the time being, we say that in the ideal state, any conductor will have different charges or normally electrons inside them, but they will be in idle state. When a certain output voltage is applied, the charges get excited and they move towards the bonds that are opposite to it so that they can complete their attraction. So if we have negative charges inside the conductor, they will move towards the positive end of the battery, and if you have positive carriers, or let's say minorities, they will move towards the negative end. Thus polarization is achieved, that one side becomes heavily positive charge, another becomes heavily negative charge, and we say this is how the external field affects the charges inside the conductor. But if we further do the analysis of the motion of charges inside the conductor, we say that it's not a straight path, or this is not an ideal situation where applying any force, let's say for this scenario negative is here or positive is here, this negative is going to push this electron to move towards the other side. So in reality, this electron is going to get stuck with hindrances inside the material itself. These could be minority charges, or these could be the structure abnormalities that could basically limit the flow, and thus it will reduce down its speed so that it can reach towards the positive end of the terminal. And this kind of drifting of the electrons inside the material is what we call as the drift velocity, and it is directly proportional to the applied electric field. So we can say that there exists a drift velocity inside any conductor when an external field is applied, and it is represented as Vd is equal to minus, showing the electron mobility is shown by mu e, and this is the electric field intensity. So this relationship is very important when we are dealing with metallic conductors and how the charges move with their drift velocity. So another thing we can do with the drift velocity is that we can introduce this factor inside the relationship of the current density with the volume charge, that will give us one variation or point form of Ohm's law. So the point form of Ohm's law is also observed when dealing with charges, especially the current density. So what is happening over here? Let us see. So we already know the relationship between the current density J and the volume charge density, or which basically tells us that how the charges are moving. This is the charges in motion. Another way to represent it. First was using current dq by dt. Another is using the current density as shown over here. Now let us replace this Vd, which is the velocity, with the drift velocity of the electrons. This is the same thing which we saw previously. Inside the conductor, we have replaced it with minus mu e, and with e, and rho e remains the same. Now let us give this rho e and mu e with a new symbol which we call as conductivity. So this is the conductivity that is basically telling us how much with energy an electron is moving inside the conductor. So this is a symbol of conductivity. Now conductivity, so the equation of the current density is now expressed as J is equal to conductivity multiplied with the electric field, where the conductivity shows how much is the electrons moving. So this conductivity is equal to minus rho e into mu e, and its unit is Siemens per meter. So this is conductivity, opposite to resistivity, which we saw in the Ohm's law. Now we can say that this equation is also known as the point form of Ohm's law. So how we can say this? Let us have a look. We know that Ohm's law is basically a macroscopic form, where we say that Ohm's law shows the relationship between voltage and current when the resistance is a constant between them. So this is at the macroscopic level. Macroscopic level means something that we can visually see. But at the microscopic level, what is happening in terms of charges and current distribution? So let us say we have a current carrying conductor and the current entering to the system is J of S. So this is the equation, and a uniform electric field is moving inside this conductor. So we know that the relationship of electric field is the voltage applied over certain length of the conductor. So keeping these things in mind, we know that the current density is represented as conductivity multiplied with electric field intensity. The current density can also be represented by its basic equation of current per unit area, and electric field can be represented as voltage per unit length, as we have seen over here. So now if we figure out the value of voltage from this equation, the voltage is dependent upon or directly proportional to the current, length of the conductor, area of the conductor, and conductivity. And if we look at a broader term, this is what? This is basically the resistance. So this is how we can say that the equation over here is also known as the point form of Ohm's law, because the resistance is dependent upon, so the resistance inside the conductor. So we can say that if you want to find resistance inside the conductor, it is going to be the ratio of the length of the conductor divided by the area of the conductor and the conductivity of charges inside the conductor. Hence we can say that this is indeed the representation of finding resistance inside the conductor, which is another way of writing the Ohm's law. Now let us look at a problem, or few problems, and see how we can apply these equations. So in this problem, we have been asked to find the magnitude of current density of a sample of a silver which has the conductivity of 6.17 10 to the power 7 Siemens per meter, and its mobility electrons is such value. What happens to the magnitude of current density? So we need to find current density when the drift velocity is 1.5, when in part B the electric field intensity is 1 meter volts per meter, and in part C the sample is a cube having a side length of 2.5, voltage of 0.4, and in part D we have a cube of 2.5 carrying a total current of 0.5 amperes. So let us start with the first part. Okay, so here what has been given to us? So we know that so we need to find the current density, okay, when the drift velocity is 1.5 micrometer per second, and what else we have? We have conductivity as 6.17 into 10 raised to power 7 Siemens per meter, and the mobility of electron is 0.0056 meter square per volt. Now we can easily apply the equation. We know that drift velocity is basically minus mobility of electrons with the electric field. This is one of the equations which we saw. And we also know that the current density is equal to the conduction with the electric field E. So these are the two equations that we have. And what we need to find is J. So we have conductivity, we can find E from V by L. So this means that electric field intensity is drift velocity divided by mu E negative. So just input the values, 1.5 into 10 raised to power minus 6 divided by 0.0056. This is a negative one, and the answer comes out to be 2.67 into 10 raised to power minus 4. So this is the answer we are getting. Now again, what happened? Keep in mind that this negative sign shows that this is an electron. So we are not going to use the negative sign over here, because negative sign indicates that this is an electron. So once we have the value of E, we can use the equation where the current density is equal to conductivity with the electric field, and thus we want to find the current density. So it is going to be 6.17 into 10 raised to power 7, the value of conductivity, multiplied with 2.67 into 10 raised to power minus 4, and it comes out to be 16.5 into 10 raised to power 3 amperes per meter square. So this is the answer of the current density for the first part. Now let us come to the second part. In the second part, we have been given the electric field intensity as 1 meter, or let us use the value 1 into 10 raised to power minus 3 volts per meter. And again we need to find the current density, so we know it is the conductivity into electric field, and this comes out to be 61.7 into 10 raised to power 3 amperes per meter square. So this is the answer of the second part. In the third part, we have a cube with a side length of 2.5 and voltage of 0.4 millivolts. So in the third part, solution to part C, we have a cube. So this is our cube, and the side length of the cube, let us say the side length of the cube is 2.5 millimeter, and the voltage is 0.5 volts. So voltage is 0.4 millivolts into 10 raised to power minus 3 volts. So this is given to us, and again we need to find the current density J. So we know that current density J is equal to the conduction with the electric field. We can write electric field as the ratio of voltage per unit length of the conductor. So we know that the voltage is given, conduction is with us, what is length? So we can write it as voltage is 0.4 into 10 raised to power minus 3 divided by length is basically side length of the cube, which is 2.5 into 10 raised to power minus 3, and the conduction value is 6.17 into 10 raised to power 7 Siemens per meter. So the value of the current density comes out to be 9.9 into 10 raised to power 6 amperes per meter square. This is the answer. Let us verify this. This is the answer. In the final part, again we have a side of a cube, but the current is 0.5 amps. So in the final part, we again have a cube, but the current given is 0.5 amps. So again current density is equal to the basic equation, ratio of current over surface area. So the current is 0.5, and what is the area of the cube? So area of the cube, if we have this cube, is length into width. So the length of the cube is 2.5 and width is also 2.5 millimeter. So this is 0.5 divided by 2.5 into 10 raised to power minus 3 whole square. So this comes out to be, because it is length into width, so I just write, okay. So it is 80 into 10 raised to power 3 amperes per meter square. So this is the answer, and this completes the solution. Let us check. It is 80 kilo, so it is 10 raised to power 3. So this is the solution to this problem.